Okay, well, welcome guys. We're gonna go ahead and get started. I posted some documents on Blackboard. If you didn't get a chance to look at those, probably want to go and open those up. I think I sent this problem out though a couple days ago, so you should already have this. If not, it is on Blackboard, or you can just look at it on the board. But what I want to do is continue our conversation on AC power. This particular problem is not particularly hard, but I like it because it's what I call a modeling problem. We're used to working with circuits, these small circuits, but here, um, this could represent a factory, this could represent some kind of commercial property, this could represent a house. In those type of facilities, you might have resistive loads, you might have inductive loads, you might have capacitive loads. So what this is got 120 volts AC, which you know is the voltage for your wall outlet in the United States. This resistive load, it says here, is a 2.5 kilowatt heater. So maybe it's a factory or some kind of commercial property where you have one of those big heaters as you walk through the door that blows out the heat. And it's resistive because those heaters work on, they have a high temperature wire that heats up and the wire turns red and it radiates heat. So you've probably seen something like that before. So you can model that as a resistor in a circuit. You have an inductive load that's 6 ohms. So that might be, if you think about a motor, all a motor is basically magnets with an electromagnet inside, and all electromagnet is a coil. So the coil is an inductor. So this might be the motor coil for an inductor. Then you got some type of capacitive load. The point I'm making is you can have a house, a whole factory, and you can take the sum total of all the resistive loads, model them as one resistor. You can take the sum total of all the reactive loads, model them as one reactance. You can take the sum total of all the capacitive loads, model them as one capacitor, and actually draw a circuit that represents an entire commercial property or industrial property. You can make a model of it. So that's kind of what this represents. But other than that, once you model it into a circuit, then we can do an analysis on it. So I have the paper, and they want us to find some of these values. So I'm just reading off the handout. It says, this is the one titled AC Power Practice 2. We did practice 1 last class. A generator supplies power to an electric heater, an inductive element, and a capacitor as shown below, as shown right here. I want you to find P and Q for each load. I want you to find active and reactive power supplied by the generator. That's going to equal the power, the sum of the powers for the loads. They want you to draw the power triangle for the combined loads and determine the total apparent power. And then they want you to find the current supplied by the generator. So I have all that listed right here. Total power, total reactive power, total apparent power. This triangle means they want you to draw the power triangle, and they want you to find the current. Now, one way to find the current is, since we know these, well, we don't know this value. We could find that value. We could find the current that way. But I'm going to show you a new way, another way to find the current without dealing with the impedance of the circuit. So what I want you to do is take out a sheet of paper, get your calculator, pens, pencils, coloring pencils, and go ahead and solve for these variables. I'm going to give you a little bit of time to do that, and then we'll go over it together, kind of work through it, and talk about the check your answers. So I'll be here. I won't be in the camera frame, but go ahead and start working on that. I'll give you maybe 5-6 minutes to do a calculation. I'll come back and we'll go over it, and then we'll move to the next part of this power stuff. So if you have any questions, just speak up. I'm right here. I won't be in the camera frame, but I'm listening to you. So go ahead and calculate, and we'll see what you come up with. All right, I'm going to give you about 2 more minutes to finish calculating whatever you're working on, and I want to go over that as a group. 2 more minutes. All right, so let's go through the calculations for this. So they want us to find the power, resistive power, reactive power, and then the total power, which is the total apparent power. And there's only one element here that dissipates power. That's the heater. Ideally, the inductive load and the capacitive load can't dissipate any power. So they want us to find the power for each load. So the power here would be 0 watts for these two. And power here, we don't even have to find it. They give it to us. They tell us it's 2.5 watts. So there's no calculation to do. Let me move the power over. So this column will be for both these reactive elements. Well, I guess I'll just do it individually. So this is P0, and this is P0. No power dissipated is heat. The only one I have is my heater. Reactive power, the total reactive power. So find the total reactive power. Again, it's just Watt's law applied to XL and XC. So let's do this one. We'll call that QL. QL is equal to, well, we know voltage and the opposition, so it's going to be V squared over XL. So if I do my 120 volts squared, my reactance is 6 ohms. Somebody let me know what you get for that.
$2,400 to $2,400.
What'd you say, 2,400?
Yes.
Okay, so we get, trying to keep my color straight here. We get 2.4. Now the units for this would be
2.4 kVAr.
yeah, kilo. Exactly. All right, so we'll put that down. Now, you got to remember, you got to write either the IND to let us know that those are inductive ohms, or put a plus sign in front of it. I'm going to choose to put a plus sign in front of it. So here, for the resistor, I don't have any reactive power, all resistor power. Here, no resistor power, all reactive power. It's positive because it's inductive. And I'll do the same thing here, but of course that'll be negative. So let's find QC. I guess I'll just change this. QC, same equation, only I'm dealing with 24 ohms. So QC, 24 ohms. Let me know how many kilobars that is.
That's 0.6 kVAr.
0.6 kVAr. So we'll add that to our list. That's a minus 0.6 kilovar. And so we found this one. We found this one. I got to get the total apparent power, just get the apparent power. So let's do that. Now, it asks for the power triangle. So let's go ahead and show the power triangle, and then from that, we can get our apparent power. So, of course, the power triangle is just the right triangle. My resistive power is 2,500 watts. My reactive power, and I got a, what's 2.4 minus 0.6? How much is that? 0.4, is it 1.8?
Yes.
1,800?
Yes.
It would be bars. I was going to write watts, but it's bars. VAR. And then, of course, you can find the apparent power by doing this. So let me know what you get for the hypotenuse here.
About 3,080.6.
All right, so there we go. So we got this. Well, they didn't ask for the power factor or that power angle there, but we wanted to find it. We could do it easily since we got all the sides of the triangle. So that's it. Now I want to show you one new thing here. I think I kind of hinted at this a little bit ago, a couple days ago. But let me show you when you find current. So you can find current, of course, since we know the voltage. We can figure out what this resistance is, right? Since we know the voltage and power, we can figure out the value of R. And you can find the total impedance for the circuit, divide that into the voltage, and you got it. You got the current, but it's a lot of work. There's a much faster way to find the current, so I want to show you that. Okay, I guess I'll get rid of this stuff. So here's what you do. There's this thing in math when you deal with complex numbers called the conjugate. And if you have a, let's say you have a complex number A, And let's say it's in polar form, it's 10 at an angle, let's say of 56 degrees. Then the conjugate of A, I will write like this, A star. Let's call it the complex conjugate. It's the same magnitude as A, but the angle is the opposite angle. So if A had an original angle, a phase of 56, then the phase of A star would be minus 56. If A had a phase of minus 66, then A star, the complex, I can't say that fast, the complex conjugate will be the opposite of that. This was negative, that would be positive. If I've given the complex number like 10 minus J 30, then A star would be 10. You just change that sign right there. If the original complex number was a minus J, then the complex conjugate would be a plus J. Okay, so you know from circuits 1 that the main way to write Watt's law is like this. Power equals voltage times current. So the AC version of this, total power is total voltage times total current. The AC version of this is that we call the total power the apparent power. So the apparent power is equal to V times I, right? But I star. And if you want to figure out the phase of this, we got
Just what the star was. I'm sorry.
the star is, if I have a complex number, so we call it A here. If I have the complex number A, then A star would be, I'll just switch the whatever sign is here. Here, the phase is positive 56, so A star would be a negative 56.
Okay.
If this was negative 56, then A star would be a positive 56. If I give it to you in rectangular form, if I give you A equals 10 minus J 20, and A star, how would I find A star? It would be 10, I just changed that sign right there, plus J 20. So the complex conjugate, what it is if you think about it graphically, it would be the mirror image of the complex number on the complex plane. If I graph this, if A is 10 at 56, maybe A is like this, then this one right here, which is a complex conjugate, would be, actually it's not the mirror image, it would be down here. The mirror image would be over here. I don't know what you call that image. I don't know what you call that. But it would be, the complex conjugate would be down here. So all you gotta do is flip the sign either on the angle or on the J operator to get the complex conjugate. So the definition you want to write, now look at this, because we never think about power as a phasor, but here we're using the phasor representation of these. The reason I'm doing that is because I might want the phase of the current, right? Now, what we get from this to find the current, what I get from this is the complex conjugate of the current. So whatever answer I get, if I want the actual current, I gotta flip the sign of the phase. So let's just do it and you'll see what I'm saying. So in DC, if I know the power, if I know that P is P times I, if I want to find the current, that's easy. I just solve this right here and say the current is equal to power divided by voltage, and I can get my current all day long. Well, I can do exactly the same thing in AC using this formula here if I understand how to use the complex conjugate. So let's do that real quick. So solving this for I phasor is S phasor over V phasor, but that's going to be the complex conjugate. So let's figure out what that is. You got all those values, you can figure out what that is. This is 3080.6, so it's 30, 80.6. Now we're treating this as if it were a phasor. We got to figure out what this angle is right there. That's why I said earlier they didn't ask us for that angle. That was interesting. Well, we need it because we want to. If we want the phase of this, we got to know where that. We got to know that power angle right there. So how would I get the power angle? Well, you got choices because I got a right triangle and I know all the sides to it, so I got choices. But typically, we just use the inverse tangent. And AC is always the inverse tangent. So if we use the inverse tangent formula, then we can easily get that. So so this angle right here, that's the power angle. It's going to be the inverse tangent of the opposite over the adjacent. So it's going to be 1800 over 2500. You might as well get rid of those two zeros to make it a little easier to put in your calculator. So you tell me what this is. How many degrees is that? And then we'll finish the problem here. Make sure you're in degrees, not radians.
I got 35.75.
35. I'm just going to round it to 36, just because I don't have room here to write the decimal. So we're going to go ahead and write this as 36 degrees. And guys, anything you turn in to me for graded stuff, make sure you're using your coloring pens and pencils. Somebody turned in something all pencil, and it was a nightmare for me to look at when I was grading last time. So use your color so things stand out. So this was 36 degrees divided by V hat they give us as 120 angle, oh that's nice, 0 degrees. So tell me what you get for the complex conjugate of the current. Let me know what answer you get.
Uh, 25.67 amps.
You said you got 0.5?
25?
125?
Nah, sorry. my connection's a little choppy. I got 25.67.
Oh, I'm sorry. 25. So you got 25.67?
Yes, amps at 36 degrees.
All right. So that's I star. We don't want I star. We want I. So I got to flip this. So the actual current phasor is the same magnitude, 25.67, but the angle is minus 36 degrees. So right away, you know, if my current phasor is at minus 36, when my voltage phasor is at 0, you know the voltage is leading the current, or the current is lagging. And if you remember Eli the Iceman, they didn't ask you this, I'm just telling you to think about it. If you remember Eli the Iceman, if the current is lagging, that means this inductor here is having more of an effect on the circuit. So, but that's it. So the new thing, the takeaway with this second power, this is power practice number 2. And the takeaway is just this, the complex conjugate formula right here. That's the new thing. So remember that formula, S equals VI complex conjugate. And you really probably should put hats on these. And I don't know, I honestly don't know if it's proper to put a hat on this. I can't remember. I mean, I had a whole bunch of this at UC engineering, and I can't remember. I might have to look that up for you. I don't know if it's proper to put that hat on it. I'm going to put it on there just to be safe, but, you know, it's just a small sticking point. It's not a big deal. But I can't remember if that's actually a phasor or not. So I'll have to look that up for you if I think about it.
Did you write equals VI square or VI star up there at the top?
That's a star.
Okay.
That's this.
Okay.
Where from? But that's a star. That looks like a 2 on the camera. or you don't know what it looks like. I can make my star like this, I guess. Does that look like a star?
I don't like. I think the other one was better. It just looked like a 2 that time. My bad.
This one looks like you see on the keyboard, but I guess a kid would probably like that one better, you know. Now, let's go to that other practice problem. Now, you're going to need a calculator, and you're going to need some paper for this one. I don't mean but this one is kind of, is trig intensive. It's not hard, but it's just a lot of little steps you got to go through. But what you want to do for this next problem, I'm looking at AC practice number 3. Now, if you don't have that, I just put it up this morning. Early this morning, I put it up. I sent you a link to it. I don't know if you looked at it or not. If you haven't had a chance to print it out, or if you don't have the capability to print, just bring it up on the screen. I'm going to try to draw the picture here. But you look at that, think about it while I'm putting it up on the board. And what you want to do, because I want to quiz you on this. I got to know if you can do this. So I would take really neat notes. So you can just, basically, since you can look everything up that I give you for a quiz, that way when I give you the quiz, you can just lay this down and just kind of work off these notes. So take good notes, make sure they're logical, and if something's not clear, then ask me about it, and I'll slow down and we'll look at it. So you look at it, I'm going to put the circuit on the board, and then we'll do it. Somebody has their mic open. It sounds like sound effects for a movie. I heard the squeaky door, the footsteps. All right, so let me put this on the board, or attempt to put it on the board. I gotta have my glasses for this. I can't see anything, and I don't have them here. Damn, it's in the car. I don't feel like going out to my car. All right, you guys might have to help me read this. I'll let you know if I need something.
Sorry.
Was that Dominic making that noise? That's 600 volts. I think that's 600. And the light bulbs, these are lights. Okay. So let me read the problem. To you. Now, I really like this problem because You know, I was telling you about the other problem we just did, that you can take a whole entire factory. It can be a commercial property. You can have a big machine. It doesn't matter. You can take really use like a factory and model it as a circuit that you can actually do an analysis on. And here's a case. Now, you know, there's no light bulb that's 12,000 watts. You can't go to Lowe's and buy a 12,000 watt light bulb. But you can have a big industrial complex or a factory where you have a bunch of light bulbs and the total power dissipated by those bulbs could be 12,000 watts. So it says lights, it's plural. So this is all the light bulbs in this building adds up to 12 kilowatts. And you guys remember when I gave you that energy project back in DC into Circus One? Some of you listed all the light bulbs in your house and you wanted to figure out how many electrons moved into and out of your house in the 30-day period. And so you had to add up all the light bulbs. So it might have been a kilowatt or a couple kilowatts if you had a big house with a lot of bulbs in it. Here we got 12,000 watts. That's a lot of lights. But you see, they lump it into one, like one light bulb, one big, huge light bulb, 12 kilowatts. And then we have an electric furnace. Now notice the furnace is resistive and inductive. So the furnace is probably like this. It probably has a heating element made of wire. And so wire, as you know from that wire resistance formula that we talked about last semester, that's where we get the heat from. When that current passes through that wire resistance, it heats up, and the wire is designed to radiate the heat instead of burning up. But then there must be a blower motor. Every motor has a coil in it. To get the motor to work, you got to have a coil. We talked about generators. A motor and generator are the same machine. So you got to have a coil in it, and electrically, to electrons or to that source, a coil, no matter what you use the coil for, looks like an inductor. So look how they model the motor. They model the motor as the furnace. This is a resistive part, probably the heating element, and then the inductive part is probably the motor, the electric motor. And then they tell you that pulls 150 amps. So we got 150 amps flowing in that motor. And notice on the diagram, they have a box around this, like this. And all that means is that's really this one unit, is one thing, and this is the internal impedance of that thing. And so you have access to. The power is probably written on the light bulbs. You can just look at the bulb, it'll say 100 watts. This, you might have to get at that to figure that, you know, the impedance of that is 2.4 plus J32, but there would be a way to get that. And that this thing, you can probably look on the label and figure out what the current is. And then we have a motor here. We have an electric motor, and that motor, they did something interesting here. They gave us the power of the motor, 80 kilowatts. So that is taking in 80 kilowatts. But then they gave us the power factor. Why would they give us the power factor? Well, you'll see that in a second. So we'll do this. So I like this because I have one circuit, but this could be a factory that's miles and miles and miles, square mileage, a really huge building. We can model it as a simple circuit like this. So there's a certain beauty in this to me. So here's what we want to find, though. We want to find, well, they have this divided up. Let me read the problem. It says an industrial client is charged a penalty if the plant power factor falls below 0.85. The equivalent plant loads are shown in the circuit model of the plant below. So this is the circuit model. They tell you the frequency. The frequency is 60 hertz. They give us that information. And they say determine the following. So the first thing we want us to find is the total power and the total reactive power in the plant. And then they say something interesting in part B. Look at part B. It says what value capacitance in microfarads is required to bring the power factor up to 0.85. So you go back to the problem statement. It says an industrial client is charged a penalty if the power factor drops below 0.85. They charge a penalty. And this is not fictitious. This is actual fact. Well, this might not be fact. But if you are an industrial client, the power company can actually charge you more money. They can charge you a penalty if your power factor drops too low. Now you might say, okay, why would they do that? What's the point of it? Okay, here's what's happening. Remember what I said a few weeks ago, or maybe a few days ago, that the power factor, is the cosine of the angle between the voltage and the current. And the cosine is 1 when this theta right here is 0 degrees. And the cosine is 0 when the theta right here is 90 degrees. So when is the phase angle between the voltage and the current? 0. Well, it's 0 when I have a resistor. So if I have a totally resistive circuit, my power factor will be 1. So this means that a power factor of 1 means that I have a totally resistive load. This is resistive. A power factor of 0 means that the phase between the voltage and the current is 90 degrees, and that only happens when I have either an inductor or capacitor. So this means that I'm reactive. This is a reactive power. And now you can see the problem. The problem is, remember what reactive power is. Reactive power doesn't do any work. Reactive power is borrowed power. I give you $1 and I take it back, you're still broke. You can't take the money and go out and do something with it because I took it back. You're broke. That's how reactive power works. Resistive power is like me giving you the power, and now I'm giving you the money, and now you can take that money and spend it on something. So resistive power is spent energy, and in order to spend that energy, something's got to happen. Like a motor's got to turn, a light bulb's got to light up. What I'm saying to you is, resistive power is the only kind of power that can do electrical work. Making a speaker sound, making an LED light. Resistive power, watts, is the only kind of power that can do work. Reactive power is basically useless. It takes up room flowing into the system, and it flows right back out. Power company they hate that. So what they want you to do is, if your power factor is like real low, they give you this threshold. And on this problem, they say, we don't want your power factor to fall below 0.85. So 0.85 is like right in here somewhere. And you can see that as I get further and further away from 1, I'm getting closer to 0, which means I'm the value of 0, which means that I'm getting closer and closer to a reactive circuit. And the energy that's flowing in is doing less and less work. But the generator producing that energy still has to kick out that energy. That's not an efficient system at all. The Duke Energy or the energy company wants this as high as possible. Now, you can't have a power factor of 1. I mean, you could, I guess, in theory. But there's always going to be some reactants in there that you can't get rid of. So the question is, or not the question, the statement and the problem is, if they're it can be up that Guys, can you still hear me?
You back now?
Okay.
Oh, yes.
But this pisses me off. Can you hear me now?
Yeah.
Is my camera back? This is what happened last time. I don't know what is wrong with this system. I was in the middle of a lecture and the camera went out. Now, can everybody see and hear me?
Yes,
Okay.
right now.
Okay, I don't know where it started to drop out at. Did you guys, when I drew the triangle, did you see that?
No.
Okay, so what we got to do is keep the power factor up to 0.85. And I was asking, how do you do that? And then the problem, he tells us how to do it because what he says is in part B, he says, what value capacitor in microfarads is required to bring the power factor up to 0.85? Well, we add capacity. What he said is we got to add, if we want to bring the power factor up, we got to add capacitive bars. Why do we have to add capacitive bars? Because in the circuit we had inductive bars. If I had all inductive bars here, or mainly inductive bars, if I want to bring the power factor up, I would add capacitive bars and vice versa. So I'm going to show you how to do that. We got to put a capacitor in parallel with this if I want to keep the power factor up above 0.85. So I'll tell you what, let's just dive into the math, and then as we go, I'll explain this. I was trying to explain it with the power triangle, but then that's when the camera went out. And is it still recording? Now I'm really, yeah, I guess it's still there. Go ahead and get your calculator, pen, paper, and let's just get into this before my camera dies. The first part you should be able to do by yourself, no problem. Now, I want to recommend something, guys. When you're doing this, is called power factor correction. When you're doing this, always use power triangles to solve the problem. So try to work off the power triangle. So what I want you to do is part A. You should be able to do part A by yourself. And you can think about part B. See if you can think about it. And I'll give you some time to do part B. I don't know if you'll figure it out or not, but if not, we'll do it together. So go ahead and knock part A out. Everybody should be able to do part A because we've done that before. Part B, I'm going to give you some time to think about how you would do that. Look at the question, make sure you understand what they're asking, and then try to solve it. And then we'll come back together and do part B together, and then we'll do part C. So go ahead and do it. I'll be quiet for a minute. I'm right here, though. You can't see me. I'm sitting right over here. And I'm going to just give you some time to work on it and think about it. And this right here, we can keep digging into this AC power stuff, but this is as tough as it gets. So if you can do this problem, you're good to go. All right, so have at that, and I'll be back here in a second. because we're gonna work about another 2 or 3 minutes, and then we'll start working on this problem together.
We don't have any audio right now. I can hear you again.
I've got to unmute my mic. Thank you. All right. So I was saying is that when I'm working these type of problems, so you got to keep a tally of things. I like to work off these lists. I just make a list of. I don't have enough room to write it, but I will write lights, furnace, motor, and I will make a list. So you guys can do that if you want on your paper. Something like this, if you were turning in to me for a grade, you want to be as neat as possible. To get a good grade, you need to be neat, because if I can't find the answer or I can't read the answer, I got to mark it wrong. So use rulers, colors, be neat about it, and you should be good to go. I want to find the total power, and so this power dissipated here, and this power dissipated there, and we can calculate the power dissipated here. So let's do that. So from the lights, let's see if I'd like to actually write this. So from my lights, you got the lights. My total, they give me 12 kilowatts. So I got 12 kilowatts. And we don't have anything there for the lights. For the furnace, I have an inductive load in the furnace and a resistive load in the furnace. So I'm going to have watts and I'm going to have some inductive power. So let's figure out what that is. Well, fortunately, they gave us the reactance and they gave us the current. So remember that this right here is the R part, and this right here is probably the coil in the motor or something, but that looks like an inductor. So I can get, for the furnace, I can get the power, I'll call it PF, but don't confuse that with power factor. The power for the furnace is going to be I squared R in the furnace. And then the QF, the reactive power, is going to be I squared XL for the furnace. So that's an easy calculation to get because they gave us the current. So I got 150 squared. The value of R is 2.4 ohms. Don't give me PF. And here I got 150 squared, and they gave me the X part of that is 3.2 ohms. So for the furnace, what is I squared R for the furnace? How many watts is that? Give it to me in kilowatts.
You want the total for both of them combined?
No, I just want for the furnace, give me this right here. I need to know the watts. You gotta keep them separate when you're doing this. So I want I squared
Yeah.
R. 150.
Yeah, that was 54 kilowatts.
All right. So everybody see what we're doing? The resistive part of the furnace, probably the heating element, that uses 154 kilowatts. And then give me I squared 3.2. That's the reactive power.
I got
How much is that?
72 kilowatts for that one.
That'll be kilo VAR, right?
My bad, yes.
And it's inductive, so it's a plus sign there, right? So I'm gonna get rid of that. We have nothing there. We got 54 and 72 kV. You can't see it, but that's kilobar. And so that takes care of this. Now the motor, they gave us the power for the motor, 80 kilowatts. So for the motor, we know the power for the motor is 80 kilowatts. But we actually have a problem with the motor. You know, inside the motor is a coil, and the coil to that generator is an inductor. So we know there's an inductive element in the motor, but how do I figure out how many bars it's using? How? I don't have a way of getting to that. Well, it turns out you do. Here's a little trick you want to do given a motor. You need to find the reactive power in the motor when they give you only the power. You want a power triangle just for the motor. Now I want you guys to think about that. Look at what's given for the motor. We know the motor, 80 kilowatts, and they gave us the power factor. What would be the reactive power for the motor? That's what you got to figure out. I'm actually going to, some of you might have figured that out during the time that you were working. But in case you didn't, I'm going to pause just for a couple minutes to give you a chance to think about how would I find the reactive power in that motor. Given the resistive power and the power factor, how do I find QL for the motor? So I'll give you about 2 or 3 minutes. If you got it, just hold on for a second. If you didn't, try to think about how you would do that, and then we'll do it together in just a few minutes. That's an important step in solving a problem like this, being able to do that. All right. I want to draw a power triangle, not for the whole system, but just for the motor. Let's draw a power triangle. Look, let's draw a power triangle for the motor. What I know is the power of the motor is 80 kilowatts. So I know that's right here. That's all resistive power. What I want to know is the reactive power. So I want to know QL for the motor. So how do I do that? Well, remember what I said about the power factor? The power factor is the cosine of this angle right here. So given the power factor, I can find the angle. If I take the inverse, if I do this, the angle is going to be the inverse cosine of the power factor. So now you want to remember that. So if I take the inverse cosine of 0.8, tell me what that is.
Got a 36.9.
36.9 degrees. So then what you can do, we know that this is the adjacent side, that's the opposite side. Well, that's the tangent, right? So the tangent of that angle is equal to QL, the opposite side, over P, the adjacent side, and they gave us those numbers. We know that this is 80. Now I'm going to just write it as 80. We know it's going to be in kilowatts. So this is 80. We don't know that, but we do know this number over here. This number is the tangent of 36.9 degrees. So we got to solve this for QL. So QL is going to equal 80 times the tangent of 36.9 degrees. So go ahead and give me that number, and that's our value for QL for the motor. So let me know what you get when you do that.
I got 60.
60 kilowatts. It says 60.
60.
60
But-
and
It's not kilowatts though. It should be.
touche, huh? It'll be kilo VAR. Everybody else doing this? You guys agree with these numbers? I think they're right. I think we're good to go. But notice that trick, what we did. Normally, when you think about a power triangle, you think about the power triangle for the whole circuit. Here, what we did, we just did a power triangle for the motor. So remember that little trick in case I give you another, that's just not a trick. I hate to say that. It's not a trick. But remember that calculation in case I give you a problem similar to this on the quiz. Okay? So now we're ready to title this up, because what we really want, we
You said
total power.
that gets a plus too, right? You said it was inductive.
Yes, it's inductive. Thank you. All inductive, so it gets a plus sign. Anything else here? I think I'm good to go. So let's get the totals of these, because that's what we're actually looking for. So I'm going to erase this. Hopefully, you got the video. You can always go back and watch the video. All right. So let's tally these up and see what we come up with. I'm missing a purple marker. Let me get another purple marker. So go ahead and add those up for me. I can do this one, I think. That's 132 kVAR. I might need your help with this. Let's see, that's 12. That's 6. And that's that'd be 20. Is it? I don't think that's right. Let me do it again. I got 6. I got 6 and 8. 6 and 8 is what? Is that 146? Is that right?
Yeah.
Okay. 146 kilowatts. So our total power, 146 kilowatts, and our total reactive power is a plus 132 kVAR. That's what we got. So that's question number 1, or letter A. So I'm going to put that off over here because we're going to need that again. So our PT, 146, and our QT, 132, plus 132 kVAR. So now what they want us to do is says what value capacitor is required to bring the power factor up to 0.85? Well, I don't know. Let's see what the power factor is now. Let's do some math with this. Now, at this point, what you want to do is work off the power triangle. And let me get my chair because I gotta write that low. I might as well just sit down. So let's make a power triangle for the whole system. Let's go ahead and do that for the whole system. So that's how you want to start to work the problem. So you go ahead and do it. And you can help me calculate since I gotta give me another calculator. I can't find my calculator anywhere. So I'm gonna start over here. And here's our power triangle for the system. My total power was 146 kilowatts. Actually, let me make this bigger. I want my triangle to be bigger. All right, my total power is 146 kilowatts. My total reactive power is 132 kilovar. Okay, so I know that. Now give me S. We can solve for this side. Go ahead and solve for that side. Let me know what you got.
I got 196.8, I guess, kVA.
All right. Now what we need is this angle right here. And you can get it. We know all the sides. You can use any trig functions. In electrical engineering, what they usually do, for some reason, they favor the tangent. So we'll go ahead and stick with that. So I know the opposite. So the tangent of the angle is the opposite over the adjacent. So if I take the inverse of that, the inverse of 132 over 146, that'll give us this angle right here. So do the inverse tangent of 132 over 146, and let me know what this angle is in here.
It's 42.12 degrees.
Actually, let me make that purple. I don't know how well these colors show up. Did you say 42.12? I'm going to go ahead and round it to 40. This is 42 degrees. So the angle is 42 degrees. So if I take the cosine of that angle, that'll give me the current power factor. So what's the cosine of 42 degrees?
0.74.
0.74. So you see what we did? If you go below 0.85, they're going to penalize you. We're down at 0.74. Now you got to remember what's happening here. the lower my power factor, the lower the angle, the higher my power factor. Because the closer the cosine, I'm looking at the computer instead of the camera. The lower, look at this angle right here. The lower this angle, as that hypotenuse, so somebody, what's going
Oh,
on there?
we're talking to each other.
Oh, okay. That's fine. Go ahead. Because I'm so afraid that my camera's going to go out and I'm seeing these things. So keep talking to each other. I don't mind that at all. As long as you're not talking about me.
All the messages
Anyway.
are recorded. You'll be able to go back and look.
I don't watch my own recording. When I look at myself on camera, I know how much I need to lose weight. So I hate to hear my voice, and I hate to look at myself on camera. So you know about that. You guys can say anything about it. I would never know. But look at what's happening. If this angle was 0, then the hypotenuse will be right on top of the 146, which means the circuit is all resistant. So I want to bring this side down that way to reduce that angle to increase the power factor. Now make sure you understand what I just said. So the question is, how do I do that? Well, we got to add a capacitor. What we got to do is get rid of some of these. Right? So what do we want our power factor to be? What do we want it to be? Well, right here. So here's what I'm going to have. I'm going to have another triangle in here. I'm trying to follow what I'm doing, please. I want to have another triangle like this, where I've taken this 42 degrees and I reduced it some. I reduced it to this new angle right here. And that new angle is going to be, well, my power factor is going to be 0.85. What angle is associated with 0.85? Figure that out for me. What angle is associated with 0.85? So you do what?
31.8 degrees.
31.8 degrees. Everybody see what he did? He took the inverse cosine of this to get the angle for that new triangle that we want that I'm showing in red. So here's what you got to do. On this
Hey, Jacob, can you hear me?
Yeah, what's up?
I was gonna ask, to find that the value for size the capacitor, will we be
Mhm.
able to do like, to use use theta equaling 32 degrees as like the tangent and
Yeah, so I did that. So we know that we needed it to be like 31.8 or whatever. So I did 146 times the tangent of 31.8 to get the
right.
other side, and
Okay,
that was like 90.5. So that side needs to be 90.5, and right now it's 132. So
cool.
I just did the difference, and it was like 41.5 different.
Right.
So I thought we need to put capacitors in, that bring that down by 41.5.
Okay, cool. Right, cool.
I don't I don't remember how to get the I don't remember how to get to the actual value of the capacitor from the power though.
And I think we just had an assignment like that on quiz two, I want to say. I'm gonna see if I can find something.
Like I have the
Will we divide it or multiply it by like 2 pi over 180, or is that something else?
Well, so yeah, I've got those equations at like xc equals 1 over 2 pi
Right,
frequency
right,
c, and they gave us the frequency, so obviously we're going to use it somehow with that, but I still don't know. I don't know how to get even to that point if all we have is the power,
right.
because I think we need to go from power to anything. We at least need a resistance value or a current, right? To be able to,
Yeah, yeah.
but I think all we have right now is the voltage.
I was gonna ask, is that what the unit is for the tangent of 32 degrees times 146?
I think that is negative kVAR is what that unit is
Negative kVAR. Okay. Oh, right.
because we're still in the power triangle thing,
Right.
and then since it's a capacitor, it's got to be negative. So hmm. No, we did do something like that on one of the quizzes or homeworks, didn't we?
hmm That, I think it was quiz two, if I'm not mistaken, but it could have been the first one too. I'm not sure.
I can't even find my notes from the power factor stuff. I've been slacking. He's right. Half the time I got it open on my workbench while I'm working.
Mhm.
Which one was quiz two? Was that the one that said test your knowledge?
Let me see if I can go back.
The quizzes were the ones that were on the actual papers that we printed out, right?
hmm
Yeah, some of these were how to get go back and forth between like XL and L and then XC and C. But
Not from KVR to microfarads.
no, there's gonna be like a couple steps in there somewhere. Yeah, we have to be able to find the current somehow, I think. Because I think the 45 or 41.5 K VAR should be I squared times XC.
That should
So
be what that equals. 41.5 should be the product.
I think
Go ahead. I'm sorry.
yeah, right, because the power equals like I squared times R, right?
Right.
So we know what this power needs to be 41.5 K. So that should equal I squared times XC, whatever the resistance
Right.
of the capacitor is in ohms. And then if we have that, then we can use the 2 pi and the frequency to find out what the actual value is.
Right.
I don't know.
VAR is a unit for power. I keep thinking that's like like the same thing as ohms, but that's okay. I get.
Yeah. There's like way too many letters in this class compared to the last one.
Yeah.
And I get so confused going back and forth between this and our math class.
Man, yeah, like, and it's funny because we are kind of on the same kind of like, we're kind of doing like the same thing somewhat, but it is a little bit confusing sometimes going back and forth between the symbols and units that they have us using because they're like completely different letters. Like,
Honestly, I would almost rather him teach us the math. I kind of like his way a little better.
yes, for sure.
He seems to make everything like way simpler.
And smoother too. I feel like her sometimes. Well, I'm not gonna say her specifically, but just sometimes in that I definitely have to watch almost every video over, not fully, but certain parts, just because it's kind of abrupt. Like it's not really a smooth transition to me how we've been going along in there. But certain things from this class have been helping me in there though.
Yeah, I agree. I had her last semester too, and it was the same. Like the DC class and that math class were pretty much right on tempo. Yep, with each other. So, but I've never heard her say, all you got to do is this. And that's the way that he teaches the math. I like it.
Mhm.
Like all you got to do is this and this. She's not like that.
No.
She gives you like 2 seconds to respond. You can't even type that fast.
I was
like, I'm
thinking,
waiting.
and
I'm waiting.
she says it like 3 times, like, "Are you guys there? Can you hear me?" And I'm thinking, like, damn, can we get a chance to like type it?
Oh, you know what? This is still recording, so this is gonna be out there somewhere.
Oh wow. Well, at least he got a great compliment. So
Yeah, there we go. I don't know. Do you see anything in your notes about the current and the power stuff or any of that?
the current power factor.
Yeah, something we can use to get from this one to the other.
I'm not sure about this one, but
Okay, so
I'm sorry. Go ahead.
I got something here that was like EC, I guess
The voltage of the
power for the capacitor equals E, which I think is our voltage
yeah, it's voltage.
phasor times IC cosine of theta. I have this on AC parallel configuration, a complete analysis. I think we did it a little while back.
Let me see if I can see that.
So I think we should be able to use the cosine of theta because it should be theta should be negative 90 degrees if we're just dealing with a capacitor. And then the voltage should be our 600 volts, I think. And we have the power. So I think if we did voltage times the cosine of theta divided by the power, that should give us the current.
Voltage times the cosine of theta.
Yeah, hold on, let me see. I think V the cosine of theta, which I think that theta is going to be negative 90. So that divided by the power should equal the current.
And so is that like putting the negative 91.2 at a phase of negative 90? Or is that not even is that not a phasor? Because I did see a formula for getting the phase current, and it was I don't know if that can be used at all though. It's the phase voltage over the impedance, but I'm not sure like if that would help either. That was like on June 29th. That was something we had on there. I don't forgot how the hell to get impedance from any of this either. I don't know if that would help either. But you said take the cosine of the negative 90 and divide it by the.
Okay, so here's the formula that I started with. Is power for the capacitor equals voltage times the current for the capacitor times the cosine of theta. So P little c equals V I little c cosine theta. And that theta should be negative 90 for a capacitor, I think.
And is PC not the same thing as VAR?
I think it should be for this. I think it will be.
Okay.
So what I have is 600 cosine of negative 90 divided by 41.5 K VAR should equal the current. Do you see what I did? I divided by both sides by I little c to move it over to the left, and then I divided both sides by PC to move to switch the power and the current back and forth. Does that look right?
Yeah, I see what you did. Yes. Okay, and then let's see what this value is.
Cosine of negative 90 is what? 1, probably? No, cosine of negative 90 is 0.
0. Yeah.
So how's that going to work then? 600 times 0
is 0.
Divided by 41.5K. That doesn't work.
No. Can we use would finding the impedance help?
Ooh.
I see one like impedance equals R plus X, and R would be 146. And X being would X be the 132 kVAR, or would we not be able to use that to get impedance and then divide the 150 by that, or no?
I'm not sure if we can use
50 divide the 600 volts by the impedance. But yeah, I'm just throwing that out there because that I'm not,
Maybe that would give us what, the total current?
the total current, yeah, would be the 600 divided by the impedance, considering that we could use the 132 and 146 as the values for R and X.
Use the 132, 146. Maybe, but wouldn't that only tell us the current like right before and right after the power source?
Yeah.
And I don't know. I mean, so what? This is a
And we
parallel
could use 132.
circuit, so the current's different in different places. Would it matter like where we put the capacitor then?
Yeah, that's what I was just hinting on, because the 132 is the combined value for the capacitor and the inductor, right? So we would have to.
Well, yeah. Right now the 132 is purely inductive because it was two pluses.
Okay.
So I think we would need to do that with the 90.5, what we need the other side of the triangle to get to, right?
Right. Okay.
But I think those two combined would give you, yeah, I mean, so did you draw the triangle that's 146 on the bottom, 90.5 on the side, and the angle of 31.8?
146 on the bottom, 90.5 on the side.
Yeah, that's like our what we want our new power triangle to look like.
Okay. No, I didn't draw it. I'm drawing it now.
Because then, I mean, we could find the total impedance will just be the or I guess it wouldn't be impedance, it's the S. What is the S? Assumed power.
Yeah, yeah.
I mean, we could find the hypotenuse of the triangle off of that.
And that's the 146 square. I mean, square root of 146 squared and 90.5 squared.
Yeah. I got 171.8 kVA. I don't know what to do with this information. I feel like every problem is like find some angles, use Pythagorean theorem. Now what?
And right now we're trying to convert it to microfarads, right?
We're trying to figure out, yeah, what size capacitor we can put in here. What size capacitor we can put in here to bring that number down. And it's got to be in microfarads. Oh, you know what?
Yeah.
Isn't it, power is V times R also, right? Just voltage times resistance is a power.
Square over R.
V squared over R, right?
Yeah.
So we could just do the power divided by the voltage and get the resistance value of the capacitor, and then we can use this formula.
The formula for impedance.
The XC equals 2 pi or 1 over 2 pi.
Okay. Cool. Yeah.
Right? So, yeah, if we do 41.5 K divided by 600 volts,
Wait. Shouldn't we be doing 600 volts squared divided by the
No, you said it's squared, isn't it? V
Yeah.
squared over R. Hold on. So the formula should be, it should say like this: 41.5 K equals V squared over R, right?
Right. V squared over R. So we would just take V squared over the 41.5 K, right? To get R. Because V squared divided by R is 41.5, and V squared divided by 41.5 should be R. Because it would
V
be,
squared. Yes, you got it. Yep. So V is what, 600
yeah,
squared divided by
41.
41,500. That equals 8.67 ohms, I assume.
Ohms, yeah.
And then if so that is XC.
Mm-hmm.
8.67 ohms. So then to get C, we need to use that other formula. Do you have that formula to go back and forth between C and XC? I think it was real early in the class.
I want to say it's pi over 180, but I'm going to go back and check again. If I have it. Because I just looked it up for that quiz, I think, matter of fact.
Yep.
Ohms to microfarads. And this is still recording. Wow.
Mm-hmm. He's not gonna listen to all this, or maybe he will, and he'll be real proud if we figured it out.
Right.
Or
Right.
he'll let us know how dumb we sound trying all the wrong things. Here we go. C equals 1 over the angular velocity, the little w, times xc.
And the that little W omega, isn't that 2 pi?
Times the frequency, right? Yeah. So the frequency is 60 hertz. So we need to do 1 over 2 pi 60 times 8.67. Right?
Times 8.67, yes. 8.67 times 1 over 2.
I got 3 0.059 times 10 to the negative 4. So 1, 4. And what was it supposed to be in? Microfarads?
Yeah.
So is that like 306 microfarads?
I'm redoing it.
Wow.
Yeah. You put in 8.67 times 1 over. Well, I put 120.
Oh, no. I did 1 over
1 over all.
and then
Okay.
all of it. Yeah, 2 pi 60 times 8.67. All that underneath of it.
Okay.
It's like,
So 3. Huh?
I typed out the formula that I have.
And what did you say you got?
I got like 3.059 times 10 to the negative 4th.
Right. Well, I ended up putting 306 microfarads after moving the decimal those.
Yeah, that's what I got. 306 microfarads.
If that's right, that is so dope that you just figured that out. Appreciate it for sure.
We'll see what happens, right?
Right.
That seems like I don't know, for as like big as all this stuff is in this problem, like huge lights and furnace and motors and stuff, doesn't that seem like a tiny capacitor to fix that kind of a problem?
Hmm.
That's like
I didn't.
306 microfarads is really, really small.
It is small. And it said generate current. No, it said what value capacitance is required to bring the power factor up to 0.85. What was the original capacity? Oh, we didn't have that one in microfarads though. The original.
Well, there was so originally there was like no capacitance in the circle at all.
Right.
I guess we'll find out. We got an answer though.
Right. And I got another class starting in 5 minutes.
All right. Well, I will talk to you. What day is next? We're not gonna see him again until Monday.
Monday, yeah.
Yeah.
Unless you
Hopefully
make an
he'll.
announcement or something.
Hope so.
I appreciate
All right, man.
it, brother. Have a good day.
Yeah. No problem. I'll talk to you later. See ya.
All right.